welcome everybody to my lightning talk on the tricuspid valve mechanics after surgical repair and in vivo study. I'd like to acknowledge my students and my co-authors. So why do this work? Well, it turns out that tricuspid regurgitation is extremely common and surgical repair is very unsuccessful, and as many as about a third of patients having some recurrence after repair within a couple of years. Why is that? We don't really know, but one idea could be that it's just the basic knowledge about tricuspid valve mechanics that is missing, and the reason being that the tricuspid valve has really been understudied. When I say it's understudied, we have been really playing catch up. There's been a number of really excellent pieces of work over the last couple of years on the in vitro, in situ, and in silico work on the tricuspid valve, but very little work on in vivo mechanics. So what we're trying to do here is really look at the tricuspid valve mechanics after repair to possibly explain what's going on that this valve failed so often and that its repair failed so often. So in this study, we implanted sonomicrometry crystals. You see them here around the annulus as well in the anterior leaflet. We're implanted in sheep. These sheep were rib covered. And during the surgery, we also implanted a suture, so-called De Vega suture, that can function as sort of a very basic cheap annuloplasty, in that when we cinch the suture, it kind of pulls together the entire valve, and we externalized the suture. So we could externally actually vary the amount of downsizing, and we could look at the sheep as we downsize the annulus and record these sonomicrometry crystals, and then compute annular and leaflet strains based on this. And see, on the right-hand side, we see what happens when we cinch this annulus. So this is one animal, and the first cinching step, which is no cinching, is baseline, and then with each successive step, we downsize the annulus more, all the way down to a very, very undersized annulus. And so what we now can do is, based on these sonocrystals, we can look at simple things like opening angle of the leaflet. And this is the opening angle throughout the cardiac cycle for baseline. And we see with each cinching step, the opening angle actually goes up, or relatively speaking goes down, meaning that it coapts before it reaches the annular plane, which would be at an angle of 0. And we could look at the maximum and minimum angles, meaning the open and closed position. And we can see that the open position actually doesn't change with cinching, but the closed position changes. And we can show that these changes are statistically significant with each De Vega step. So annuloplasty actually reduces the amount of angle, or the degree to which the leaflet changes throughout the cardiac cycle. We can also show that the velocity changes, and so this makes sense. If there's less angle being traveled over the cardiac cycle, then the velocity also goes down, and we can show this statistically significant for each successive De Vega step. So not only does the opening angle change, also the opening and closing velocity changes. We looked at the leaflet strains and found that in circumferential direction, after the first cinching step, actually the strains go down. And so very importantly, we compare here the strains relative to end-diastole. That's why they're all at 0. And we can also show that in radial direction. And here it's a little less unclear. For the first step, it goes kind of up. We see also that that falls within sort of this error margin. So I wouldn't put too much trust into that. But overall, the trend is towards smaller strains. And when we look at aerial strain, which in a sense is a product of the two, we see a clear trend where baseline we have high strains, and then those strains go down throughout the cardiac cycle and with each cinching step. We can quantify this a little more in a bar graph. So here we show the end systolic strain relative to baseline. So we look at each cinching step and compare the strain to the baseline step. So a negative strain means that relative to the baseline, there's less strain, right? And so we see that with each cinching step down here, these strains become more and more negative. Or in other words, the strains are less and less high. And this is the aerial strain here in pink. And in gray, we have the radial strain. And so it's pretty clear that this aerial strain is driven by changes in radial direction and not circumferential direction, which essentially stays close to 0. And again, we can show that this is statistically significant. So what did we learn from this study? Very important. Tricuspid valve repair via annuloplasty changes the opening angle. In other words, it reduces the opening angle. It lets the leaflet not close all the way. The overall velocity goes down of the leaflets. It turns out that the strains drop anisotropically, more in radial direction, circumferential direction. And it turns out that in a secondary analysis, we found that the reduced strain correlates with annular reduction of the anterior annulus. So the more we downsize the anterior annulus, the less strain we have throughout the cardiac cycle. So what are the consequences? Obviously, less strain means that there's a disruption of the mechanobiological equilibrium. The consequences are not known, but we can imagine that a change in these strains will actually change so that the phenotype of these resident cells and could have overall potential remodeling consequences that then could be detrimental to valve function. We thank the American Heart Association for their support. And if you have any questions, please shoot me an email. Really appreciate it. Okay, and bye.